This is a supplementary video for the paper titled Smooth IMU Propagation with Jointly Distributed Poses on SE3 Manifold for Accurate and Robust LiDAR-Inertial Odometry. In this paper, we address the limitations of existing IMU propagation methods in terms of motion prediction and motion compensation. For motion prediction, the existing methods typically represent a 6-do-F pose by separating rotation and translation and propagate them on their respective manifold, so that the rotational variation is not effectively incorporated into translation propagation. For motion compensation, the relative transformation between predicted poses is used to compensate motion-induced distortion in other measurements. But since predicted poses inherently contain errors, this introduces uncertainty in the relative transformation. To tackle these challenges, we propose a smooth IMU propagation with jointly distributed poses on the SE3 manifold. This paper consists of 4 key contributions. First, we represents and propagates the pose on SE3 manifold, where the propagated translation properly accounts for rotational variation, leading to more accurate motion prediction. Second, we introduce an uncertainty-aware motion compensation, or UAMC. We precisely characterize the relative transformation uncertainty by considering the correlation between predicted poses, and incorporate this uncertainty into the measurement noise during motion compensation. Third, we present a LiDAR-Inertial Odometry framework, referred to as SE3 LIO, that integrates the proposed IMU propagation and UAMC. Finally, we validate SE3 LIO using data collected in diverse scenarios. First, we evaluate our method on the SPMS sequence of the NTU viral dataset. This dataset was collected using a drone equipped with a low-channel LiDAR and involves aggressive motion, where the rotational and translational speeds exceed 1.6 radians per second and 5 meters per second, respectively. As shown in highlighted area, SE3 LIO exhibits the least drift. Second, we evaluate our method on the CW sequence of the R dataset. Our dataset was collected using a ground vehicle in large-scale rough terrain, featuring fluctuations due to uneven terrain and degraded measurements due to dense vegetation and extensive open spaces. SE3 LIO maintains robust and consistent performance throughout the entire trajectory.